Hello everyone, this is Sam from class, and I'm here to talk a little bit about Aldol reactions and the Zimmerman-Traxler transition states and how we can draw these both in a diastereoselective fashion and in an asymmetric fashion. So in class, we learned about the diastereoselective version of these Aldol addition reactions. And before I talk about what happens when we have a chiral auxiliary on our substrate, I first want to review just a little bit how we draw these Zimmerman-Traxler transition states. So let's look at a basic Aldol reaction. And I'm going to take this ketone right here, and I'm going to treat this with LDA. And you're going to have to forgive me for being left-handed and covering up some of these drawings. That's just the way it is. So first what I'm going to do is I'm going to treat this with LDA. And it actually doesn't matter if I use kinetic or thermodynamic conditions here because I've only got one side that I can form the enolate on. But typically we do this in THF at -78, so I'll just write that in there. And then what I'm going to do is once I've formed my enolate, I'm going to treat this with an aldehyde. I'm just going to make one up. Okay, let's say we use some sort of aliphatic aldehyde like this. So, the first thing we always need to decide is, are we going to form an E enolate or are we going to form a Z enolate? And because the ketone we're using has a bulky R group, on my pen, okay, there we go. Because we have a bulky group here, we consider phenyl as bulky. What this means is we're going to get the cis or the Z type enolate. So what that means for me is I'm going to get this enolate right here, where I have this benzyl group on the same side as where my O- is. So that's of course the Z and or cis type enolate. Okay, and that's simply because of that bulky pH group. So now what's going to happen is I'm actually going to color code my aldehyde here in blue. We're going to form the enolate and then we're going to add the aldehyde to that enolate. And we're going to see what our Zimmerman-Traxler transition state is going to look like here. Okay, so these are the intermediates. They're going to come together. And so, to draw these Zimmerman-Traxler transition states, I highly recommend finding a pencil to do this when you're doing this at home. I'll be doing it in pen today because I want to make sure you can see what I'm writing, and a pencil might be a little light. But doing it with pencil is a great way because you can easily erase things and fill in the groups as you go. And if you make a mistake, obviously you can easily recover from that. Now before I draw this, I want to point out something that you should always remember with these Aldol reactions, and that is that Z enolates give syn Aldol products. And so when I'm drawing my Zimmerman-Traxler and I'm deriving what my product is going to be, I already know it should be a syn Aldol product, and that's going to help me kind of make sure that I'm on the right track as I'm going through this. So that's one thing to remember. Z enolates always give syn products. Okay, so for the Zimmerman-Traxler, I need to draw my six-membered ring. So it really doesn't matter how you do this, and that's why I like doing this with pencil, but I'm going to start drawing it this way, where here is the double bond of my enolate, and it's going to be attacking the aldehyde, which I'm going to do in blue. And I'm going to stick my hydrogen here in the pseudoaxial position because that is the smaller group, and that means that this propyl chain will be coming over here, and it's kind of in the least sterically hindered environment, so that's why I want to put it there. Now for the O- of the enolate, that'll be back here. And of course that's bound to the lithium cation, which is also binding to my aldehyde oxygen, and that's what really organizes this entire transition state. And because it's a Z enolate, my H is going to go here, and the benzyl group is going to go right here. So I can see that the pH and the H are cis to each other, just like they're cis in the original enolate. In my original drawing, these two groups right here are cis to each other, so they need to stay cis here. And I can also see that the oxygen and this benzyl group, I know it's a little hard to tell, but they are also cis to each other. So this is what my Zimmerman-Traxler transition state is going to look like. And if I unravel what my product is, I can do that. And so it's going to look something like this, where now that double bond has now been downgraded to a single bond. The benzyl and the H group are still in the same position. I'm coming up to where my aldehyde used to be. It's now become the OH group. And I have this H coming up, and then I've got my propyl chain coming out. And then in the back, I've got to fill this in. I've got my phenyl group right there. And then my my carbonyl, now this is upgraded back to a carbonyl, is going to be right there. Now there's a couple of ways that we can now unravel this into the final product. We can either assign R and S configurations to the two stereocenters, one being right there and one being right there. Or you can also just kind of look at it from a different perspective on the page and unravel it in your head. I usually try to do both when I'm doing these, just as a way of double checking myself. I'll do the R&S configuration though, because that's just easier to do on paper. Okay, so for this stereocenter right here, I'm going to call the group going up to the carbonyl group 1. I'm going to call the group coming over to the hydroxyl group 2. And this is going to be group 3, the benzyl group. So it looks like I'm R, but if I'm looking at it from this side, that H is coming out at me, so this is actually going to be an S configuration. And for this stereocenter, obviously the hydroxyl is going to be group 1, this branch is going to be group 2, and then the propyl chain will be group 3. So it looks like S, but if I'm looking down on it from above, it's actually going to be R. So now what I can do is I can go ahead and translate this into my final structure, which I'll use this 3 lines as the equivalent symbol. And I'm going to draw it this way, where my ketone is over here on the right side of the molecule, because that's really how my reaction scheme started. And what I need to decide is my phenyl group, or my benzyl group rather, on a hash or a wedge, so I'll decide that in a minute. And then in blue I've got my propyl group, so the OH is going to be on this carbon, and I've got my propyl group coming off here. So what I need to figure out is the OH and the benzyl are they on wedges or are they on hashes? I know that they're both going to be the same, because again, it's supposed to be a syn-aldol product. So I'm not going to get a wedge and a hash. They're both going to be either hashes or wedges in this particular instance. So what I'm going to do is I'm going to start with the hydroxyl, and I can already tell that it needs to be on a wedge if I'm going to get the R configuration. Okay, so that's going to be there, and I can already see that I'm going in this direction, H is going back, so that'll be in R configuration. For my benzyl group, that needs to be S, and I can already see that that also needs to be on a wedge, and that actually confirms that it is a syn-aldol product, so I did this correctly. So I can see if I'm going this way, H is going away from me, and so this is S, so I did this properly. And that's actually the final product from this reaction. But one thing I want to point out is that it's racemic. Okay, so we're getting an equal mixture of the enantiomers. So I'm getting the double wedges and I'm getting the double hashes. And those are the two products I'm going to get. Those are both syn-aldol products. Okay, there's nothing really controlling the absolute stereochemistry here, although I am getting good diastereoselectivity. So that's how we do a Z-enolate and we draw its Zimmerman-Traxler transition state. Let's take a look at an anti-enolate product. So I'll go to a new page here just for a little bit of extra practice. So let's say I had a ketone like this, so very similar to the one that we had before. I've only got one site where I can form an enolate. And I'm going to use slightly different enolization conditions here so that I can get the trans or the E-type enolate. I'm going to use the dicyclohexyl boron chloride Lewis acid. I'm going to use triethylamine, and we can do this in dichloromethane as a solvent. And that's going to generate the E-type boron enolate. Now, last time we said that this phenyl was bulky, and that's why we got the Z, because the group actually wanted to be up here to be away from the phenyl. But now we're using a really huge Lewis acid here, so that's going to override that, and we're going to get the methyl now coming down, and we're going to get the E or trans type enolate. And really the reason for this is because of these really bulky cyclohexyl groups. So this methyl group wants to be far away from that. Now, once I generate this enolate in a second step, I want to treat this with benzaldehyde. That's going to be my aldehyde here, and again I'm going to try and do these in blue. And now I want to see what type of transition state and product we're going to be getting here. Now, just like with the Z enolates giving us the syn-aldol, this is an E-enolate, and E-enolates always give the anti-aldol product. Okay? So right out of the gates, I already know what kind of product I should be expecting from this diastereoselective aldol reaction. And that's just going to help guide me through this problem. So this is going to be combining with my benzaldehyde. And these will be my intermediates. So once I form that enolate, I'm just going to syringe in some of that benzaldehyde. And let's see how we're going to predict our product. Let's see what the Zimmerman-Traxler transition state looks like. Okay, so once again, I'm going to draw my enolate in this form. It's going to be interacting with the benzaldehyde, which I'll do in blue. And again, as per usual, I'm going to put my small group in this pseudo-axial position to minimize steric strain, put the bulky phenyl group in the pseudo-equatorial position. And I still have a phenyl group, just like with the last problem we looked at, in this position here. And then I've got the O- hanging out here in back. That's bonded to the boron, which is also going to bond to the aldehyde. And then I've got a cyclohexyl group in each of the two positions. The pseudoaxial would be this one, and then this would be the pseudoequatorial. Now, in this case, if I go back to my original enolate, I can see it's trans, so the methyl needs to be away from the oxygen group. Or another way of saying that is the methyl and the phenyl now need to be cis to each other. I can already see the phenyls pointing up in this direction, so my methyl is also going to be pointing in that direction as well, and that'll put the H right here. So if I can go ahead here and translate this, or convert this rather, into product. Once again, I can drop everybody in the same position. I just need to change my bonds. So the double bond of the enolate here is becoming a single bond. I still have that phenyl group there. I've got an H here, I've got a phenyl here, and the double bond of the aldehyde has now become my hydroxyl, and the single bond to the oxygen in the enolate has now been restored as a carbonyl. Okay, so this is going to be my product here. Now let's go ahead and assign R and S configurations. So for this carbon right here, this will be group 1, this will be group 2, this will be group 3. It looks like R, and if I'm looking down from above and the H is going away from me, it'll stay as R. If I look at this stereocenter here, OH is going to be 1. This chain here going towards the carbonyl will be 2. Phenyl will be 3. Well, actually, no, wait a minute. Phenyl is going to be group 2 because that's going to have 4 carbons. This one's only got 3. So this looks like R, but if I'm looking down from above, it's going to reverse. So this is actually going to be an S-configured stereocenter. Okay. Remember, we're treating phenyl as group 1 here, so that's why it goes from the OH to the phenyl to the chain. Looks like R, but H will be coming out, so it's S. Let's go ahead and translate this into product. So once again, I'm going to start by drawing my ketone over here. And my phenyl group of the aldehyde is going to be here, and I need to decide, is the OH on a wedge or a hash? And I can already tell it needs to be on a wedge if I'm going to get the S configuration. And you can see here, I'd go from OH to phenyl to chain. H is going back, so that's going to stay as S. Everything looks great. Now, for the methyl group over here, I can already tell that needs to be on a hash. And if I do this, it looks like S, but H is coming out at me, so it's actually R, and I've successfully converted that over. And you can see it's an anti-Aldol product. I already knew that going into this, and that gives me some confidence that I've done this correctly. I want to remind you that this is going to be a racemic reaction. We're going to get the mixture of the two enantiomers, so the other product being where the OH is on a hash and the methyl is on a wedge. We'll never get the double wedge or the double hash product here because those would be syn-aldol products, and we can't get that here because I had a trans-enolate, right? So you need to follow those rules. E-enolates always give anti-aldols, Z-enolates always give syn-aldols. Okay, so now the big question is, what happens when my carbonyl compound has a chiral auxiliary on it? So what if this was chiral, which in terms of my Zimmerman-Traxler would make this chiral? That's the big question. So let's see what happens.